So it is based on two categories: chain polymerization, which is also known as addition polymerization, step growth polymerization, also known as condensation polymerization. We'll look into detail why chain polymerization is also known as addition polymerization, whereas step growth polymerization is also known as condensation polymerization. So, to begin with the classification, first is chain reaction polymerization. That is also known as chain growth polymerization and addition polymerization. This is so called because this method involves the repeated addition of monomers to produce long chains. That is, there is a repetitive addition of one monomer to another to produce long chains. And in doing so, there is no elimination of any byproduct or small molecule. In other words, we can say that this is the successive addition of monomer molecule onto the reactive ends of the growing polymer. Like as if a polymer is growing and to its reactive ends, monomer goes on adding. This is just similar to like we increase the length of some chain by linking some additional links into it. So that is why it is known as chain growth polymerization. In this type of polymerization, the monomers must have a double or triple bond. That is, for addition reactions, unsaturation is mandatory. That for a monomer to undergo addition reaction, there should be a double or triple bond, that is unsaturation. So maximally alkenes will be discussed in this category. The molecular weight of such a polymer is an exact multiple of the molecular weight of the monomer. In a way, we can say that if n number of monomers have joined together, the molecular weight will be n into molecular weight of a monomer. This is so because the process involves successive addition of one monomer to another without the elimination of any small molecule or byproduct. Lewis acids or bases, that is, the active species, radical initiator, they behave as catalysts in addition polymerization. We look into this, how these radical initiators help in the addition polymerization process. Next, the mechanism of polymerization takes place in three distinct steps. One is chain initiation step, the other is chain propagation step, and the third is chain termination step. We'll look into this step one by one. For the chain initiation step, that is for the mechanism of chain reaction polymerization, we need active species. Active species means that can activate a single monomer so that it can propagate a chain. This active species can be a free radical, it can be a cation, or it can be an anion, just to initiate the polymerization. This active species will attack the monomer's carbon-carbon double bond and will activate the monomer to propagate the chain, that is to attack further more monomers. This active species is generated via an initiator molecule. The initiator molecule gets thermally decomposed or it undergoes a chemical reaction to generate the active species. As we can see, this is the initiator molecule. It undergoes the homolytic fission to generate the active species. This I is to generalize or a common notation for active species, may it be free radical, may it be cation, or may it be anion. This initiator produces active species which further attacks the monomer to generate the active monomer. That is, when this active species attacks the carbon-carbon double bond of the monomer, this monomer is activated and a new active species is generated. So this is known as chain initiation. So the initiator molecule, the initial monomer, becomes the first repeat unit in the incipient polymer chain. That is, what unit is repeated one after the other to lead to a chain. Next is chain propagation step. This newly generated species, that is the active monomer, adds on to another monomer in the same way as in the initiation step and produces a larger radical. This larger radical further adds on to a monomer molecule and the chain continues. In the final step, that is in the chain termination step, two active monomer chains, two active chains, they unite together to form a neutral polymer. So these active centers are removed or they combine with each other and the chain propagation comes to an end. To look into the example of chain growth polymerization, amongst free radical polymerization, cationic polymerization, anionic polymerization, free radical polymerization is the most common. So to take up the example for free radical polymerization, here I'm discussing the example of polymerization of ethylene. In this, for chain initiation step, the initiator molecule taken is benzoyl peroxide that undergoes homolytic fission to generate a benzoyl radical. This benzoyl radical attacks to the carbon-carbon double bond of the ethylene to generate or to activate this ethylene unit so that it can propagate the chain. So this is how the chain propagation takes place. That is, this active monomer generated from the attack of radical on the double bond of the ethylene further attacks another monomer, that is the ethylene unit, to elongate to produce the larger radical that can propagate the chain. Finally, in the chain termination step, the active chains combine together, the two radicals combine together to form a neutral polymer. So this is how free radical polymerization takes place. Now, there are certain important characteristics of addition or chain polymerization. Once this initiation occurs, the process is so fast that the polymer chain is formed very quickly in very less time. Since this addition reactions, during these addition reactions, that is, during this polymerization process, the carbon-carbon double bonds, the carbon-carbon double bonds in the monomers, they are being converted to two single carbon bonds. And so energy is released in this process. So on the whole, this polymerization process is exothermic in nature because carbon-carbon double bond is being converted to two single carbon-carbon single bonds. Next, the chain reactions normally afford polymers with high molecular weights, that is 10 to the power 4 to 10 to the power 7. So these are the characteristics of addition and chain polymerization. Next in this category is condensation polymerization. Condensation polymerization is so named. This polymerization reaction involves series of condensation reactions, that is the step-by-step reaction. It involves the functional group of the two monomers to interact with each other, and finally the elimination of small molecules takes place, may it be water, ammonia or HCl. So this is then known as condensation polymerization because it involves the elimination of small molecules. The essential condition for this polymerization is the presence of two or more reactive groups or double bond in the monomers so that the interaction can be made feasible. For an example, I'm taking up the condensation polymerization of nylon 6,6. Nylon 6,6, we are all familiar, is a common polymeric clothing material and it involves two monomers. hexamethylene diamine. As it clears, this is hexamethylene diamine and adipic acid. This is so called nylon 6,6 because both the monomers have 6 carbon atoms. Each monomer has 6 carbon atoms. Two monomers, that is hexamethylene diamine and adipic acid, react to form a dimer of nylon 6,6, and the process involves the elimination of small molecule, that is water. Now at this point, when this nylon 6,6 is formed, at this point, the polymer can grow further in either direction. It can grow via this direction also, and it can proceed via this direction also. That is, it can proceed via carboxylic acid group also, via this group also, that is NH2. This chain can grow in either direction by bonding to another molecule of hexamethylene diamine or adipic acid or to another dimer. So this is how condensation polymerization takes place. To go through a very important thing, that is the characteristics of step polymerization or condensation polymerization. This process is repeated throughout the polymerization mixture until all the monomers are converted to low molecular species such as dimers, trimers, tetramers, etc. That is, this process goes on until all the monomers are involved in the reaction and ultimately they result in the formation of dimers, trimers, tetramers. These molecules, which are called oligomers, in the previous lecture also I mentioned that when 2, 3 or 4 monomers are uniting together, they result into smaller units that are oligomers. These oligomers can then further react with each other through their free functional groups to result into larger polymers. Polymer chains that have moderate molecular weights, not very high molecular weights, polymer chains that have moderate molecular weights can be built in this manner. The high molecular weights common to chain polymerizations, as we discussed in the chain growth polymerization, we can get polymer chains that are of high molecular weights. We cannot reach up to that point in this type of polymerization because as the molecular weight increases, the concentration of the free functional group decreases dramatically, because unless and until we have free functional groups, we cannot proceed towards further steps or further condensation reactions. So as the concentration of the free functional groups decreases, the reaction stops there only. Next, in the category of characteristics, the polymer chain forms slowly, sometimes requiring several hours to several days in comparison to chain growth polymerization, where it takes place very quickly. Since most of the chemical reactions employed have relatively high energies of activation, the polymerization mixture is usually heated to high temperatures. So high temperatures are needed for this type of polymerization. Branching or cross-linking does not occur unless a monomer with 3 or more functional groups is used. Because if we have 2 functional groups, it proceeds in linear direction. Branching or cross-linking does not occur unless there are 3 or more functional groups. So we are now in position of differentiating addition polymerization with condensation polymerization with a level of understanding. The method, that is the addition polymerization, involves the repeated addition of monomers to produce long chains without elimination of any byproducts. Whereas in condensation polymerization, the method involves series of condensation reactions, generally involving 2 monomers with the elimination of small molecules like water, ammonia, or HCl. In addition polymerization, monomers must have a double or triple bond. That is, to undergo addition reactions, presence of double or triple bond is mandatory. In condensation reaction, monomers must have 2 similar or different functional groups that interact for the elimination of smaller molecules. The molecular weight of the resultant polymers in case of addition polymerization is a multiple of monomers' molecular weight. That is very simple because this is just the repeated addition, that is the successive addition of one monomer with the other. Whereas in condensation polymerization, the molecular weight of resultant polymer is not a multiple of monomers molecular weight, because it involves condensation reaction, which includes the elimination of small molecules. In the case of addition polymerization, for the activation of the double bond of the monomer, Lewis acids or bases or radical initiators are catalysts that are required to initiate the reaction in case of addition polymerization. In condensation polymerization, we just require functional groups, no such catalysts are required. High molecular mass polymers are formed at once in case of addition polymerization, while in the case of condensation polymerization, the molecular mass of a polymer rises steadily throughout the reaction, because this is the step polymerization. The examples of addition polymerizations are polyethylene, Teflon, polyvinyl chloride, that we shortly name as PVC, etc. Whereas for the condensation polymerization, it is nylon 6,6, polyesters, perylene, etc. In the next session, we'll be continuing with the classification series, and we'll be discussing classification based on tacticity and classification based on molecular forces. Thank you.